Hi folks, welcome to another episode of NYC CNC. Today I wanted to talk about this aluminum fixture I made. I use it to shorten up these shoulder bolts, and they have a 1/4 inch shoulder but a 1/2 inch thread, and I need a 1/4 inch thread on them. So what I do is this will hold up to 10, and you just pop them in the fixture, and then that'll go in the Tormach CNC mill, and I can machine off 10 of them accurately in one fell swoop. I make a lot of things like this out of aluminum for two reasons. One, I have a lot of aluminum, and so it's easy for me to feel like I'm not dipping into precious resources there. And it's a lot quicker to make something and just, sometimes I don't know. Sometimes I end up using things for years, and sometimes they get scrapped because I improve the design or I end up using it for a different part. So I made this one a few weeks ago, and it works great with one exception, which is that, and I remembered this after a Facebook buddy posted on the NYC CNC Facebook page, which you should check out, remembering that when you do something like this, when you're machining down existing threads, you want to do so in a threaded secured position so that when you back the part out of the fixture, you'll actually re-chase the threads back out. So this fixture was a quickie. As you can see, I just machined I actually bored this out, or reamed it so it has a really nice fit, and then machined out enough pocket for the head itself of the shoulder bolt, like so. And then I just took the bandsaw and ran a split line down it, so when you stick this in the vise and you squeeze it, you've got plenty of clamping force. So that part of it works great. What doesn't work great, let's take a look at a finished example. You can see here nice surface quality on the top of it, which I like that. That's always nice to see. But it raises up a burr, which I don't like. Now, once that happens, you can do a few things to fix it. You can re-chase it with a die. You can use a thread file to file it down. Or you could also just stick it on a belt grinder or belt sander and chamfer it yourself. But those are all clunky solutions that I don't like, and I want something that's more automated. So let's hop over to a Libre and take a look at the CAD here for sort of version 2 of this that I've designed that we will make out of steel. Okay, I've got the model open in a Libre, and you can see it looks similar. Got the split line running down the middle. I've actually got a shoulder bolt modeled in it right here. This is an assembly file. We'll go ahead and edit the fixture itself. And here we go. Now, the difference here is I'm not creating a larger, wider pocket for the head of the bolt, but rather just a bored area or reamed for the shoulder, and then I've got the area here that will be threaded. I went ahead and modeled the threads in the first position using the helical cut, and I had not done that before, and I found it wasn't hard once you figure out a couple tricks. So if you want to see a video on that, click right here and hop over. I just published a second video covering how to do that. Otherwise, just kind of cool to show you the idea so that, again, this part will be made out of steel. So once you thread it in, you'll have plenty of clamping force from the split line and the precision hole here. And then when you back the part back out, it should chase the threads, and they should be nice. They still may need touched up or taking the edge off a little, but I think it'll be a nice result. Okay, so let's take a look at the model. We start out with a 1.5 by 6 inch chunk of steel, and let's see here. There's the first hole, which is 257. So that's the nominal diameter for tapping a 5/16 by 18 thread pitch, which is what this is. And the second hole, as we just see there, this will be 375, like so. That'll support the shoulder of the shoulder bolt itself. And we create a new plane that has to do with the helical cuts. And then there is our bandsaw line that runs down the part. Again, this is so that when you squeeze in the vise from this end and this end, you'll create the clamping pressure on the shoulder of the shoulder bolt. And we add our helical cut to make it look cool, and you can kind of get an idea of what the thread is. And then we just repeat that down the row. You can repeat the helical cut, I believe, as well, but my computer doesn't really have the horsepower to handle that well, and it's certainly not necessary. And also, if it's not obvious, the actual threads will not be in this position. It's on a Tormach with a tapping compression head. It's arbitrary where your thread start is, and even if you thread milled it, you could control the start, but you wouldn't even thread mill using this geometry, at least so far as I know. So again, it's really just cosmetic. So that's a quick overview of the CAD of the part. I thought what we would do is hop over to the mill and mill this out. I'll of course hop into Sprute Cam first, and then make the fixture, and then we'll machine some parts and see how the set screws turn out. Okay, I've got the part modeled up here in Sprute Cam. It doesn't really get any easier than this. We're going to start with a letter F drill, which is the pre-drill for the 5/16 by 18 tap. So we're going to run that all the way through, which you can see like so. And then the next thing, we'll do a 2D contour to machine out the pocket of the larger hole there. I'm going to go ahead and just interpolate this. If it were a different situation, I could see setting up either a reamer, which wouldn't go to the full, can't ream into a square corner like that, or you could do a boring bar and you could get pretty darn close. But this will be fine because the split clamp nature of it. There'll be plenty of clamping force from an interpolation, which inevitably will be, no mill, let alone a Tormach, interpolates nearly as round a hole as a reamer or a boring bar, but it'll do fine here. And you want to make that pocket first, obviously, because you don't want to tap through this whole block. You only want to tap through what you need to. So we'll go ahead and hop back to the simulation, and you can see right here, wrap it up to it. So, boom. I think that's a 1/4 inch end mill, and there's our tapping operation. So then when that's done, we'll hop over to the bandsaw, we'll cut her in half, and we'll have our little fixture. So let's make some chips. Okay, I've got a piece of steel here in my vise. I happened to find a piece that was 1.5 by 5 1/4 on the X, and just a little under a 1/2 inch, and when I faced it down, it faced out to 425 thick. It's worth it to me to use this piece of scrap because it's the closest thing I've got. So I tweaked my CAD just a hair. We lost one hole, not a big deal, and we're going to have a little bit less engagement on the shoulder bolt shoulder itself. We'll still have the full 1/4 inch thread engagement here, but not a big deal. So let's go ahead and set our 0 with my favorite tool here in the world, this hammer. There's our Z0. Now the X and Y are very imprecise on this part. The Z matters, but the X, Y don't. I'll still set them. Okay, I always like to do a sanity check. That's about the center of my first hole. Center of my last hole looks good. Let's throw in a letter F drill. And my coolant lines set up. Let's rock and roll. Okay, looks like we did tap all the way through. Let's grab a shoulder bolt and see how she fits. Let's zoom in on that. We may need to use a driver. Let's see how she fits. Okay. Perfect. And it won't cover the full depth of the shoulder right now because we had a shorter workpiece, so that's about 1875 instead of 250. That's okay. Got a little bit more out of it. That's fine. It looks like a nice fit though in the hole, which is perfect, and the threads look good. So I am very happy with that. Let's take it off and we will run our slot through it on the bandsaw. Okay, we're over at the bandsaw. Let's cut our split line. Okay, let's head back into the machine shop room and we will take a look. Okay, I just used air compressor to blow the chips off and ran a file over it to knock the burrs down. It did split open a little just from the natural steel relief as I split that line, but I bet our threads are going to be okay. And I have not tried this yet. This is all for real time here. Yep, even though that thread is split open a little bit, it's threading in great, which is just what I wanted to see. Go figure, I only have 4 shoulder bolts left, but I got an order of 250 coming tomorrow, so I want to get this video done up, and so you're only going to see me machine down 4, but certainly no difference on that aspect of it. Get them all started here. Actually, it's kind of nice that the piece split open a little because they thread in easily. Now this does take longer to load than the other fixture I made where you just pop them in and pop them out, but I'll tell you, if this works well, the reduced amount of cleanup time post trimming is going to be well worth it. So we will seat those against the shoulder in our part, and let's see here. Just for kicks, let's see. Yep, not half bad. I like that. And we'll actually use this parallel and the shoulder bolt head in our vise. Okay. Now when I'm fully loaded, I still leave this little tail piece outside the vise that I'm trying to pinch on the split line portion of it and clamp down. I will tell you those are not going anywhere. Okay, now we have a 1/4 inch of thread, so we basically want to machine this down flush. Now I'm a little embarrassed, I use a beater end mill to do this, so you guys might yell at me or not like it, but tough, because it works fine and not always pretty though. We'll take a look here and see how it does. Okay, let's touch off. Come up a few thousandths and get our coolant on here. Okay, per G-Wizard, we're going to do 2,700 RPM at 14 inches a minute. That's about 0.7 horsepower, and it's a 1.4 thou chip load per tooth. I actually just realized I'm still on my low spindle belt, so let's switch it back here to high real quick. Okay, back to high spindle mode, 2,700 and about 15 inches a minute. Coolant on, here we go. Okay, let's take a look. Okay. Really nice surface finish. I like that. Now let's see how they back out. Ooh, that's nice. Okay. We do have a very small burr. Let's see how the rest of them look. Okay. Same thing on that one, actually maybe a little better. You can see a little burr. Okay, that one looks good. Again, just the tiniest burr. Looks pretty good. Let me go grab a test piece to thread these into. This is my little plasma cut bracket that I'm going to test them on. And if you actually want to see how I make those, here's the little fixture plate for them. And there's a video which you can click on right here. It'll show the process of machining these, which I tell you, I love making parts, and I love making parts with fixtures. It's just cool. So let's see real time how she does. Hey, that's awesome. That's really great. Threads right on. Let's see how the other three do. Before, I was having to chase these with either a thread file or a die. Now this one I can feel a burr on it. I bet this one won't go. Oh, nope. Boy, it did. And now you can see, look how nice that looks. Nice and flush. You can run your finger over it. There's a tiny burr, but it's not going to cut you. In fact, not going to cut you at all. Okay, so 2 for 2. Oh, that was easy. That popped right in. No problem there. All right, last one. Oh, it's right there. Guys, that's a winner. I am really happy with that. So that's a wrap for today's episode, folks. If you've enjoyed this video or learned something, please comment below, like it, and share the video. Check us out on our Facebook page. I tend to throw up some decent pictures there and whatnot. Otherwise, that's all I've got for today. Stay tuned for more, though. Take care, folks. I will see you soon.